Okay, finally, we're going to talk a little bit about the limitations of the method now that we know how the method works. And so we're going to talk about stability in detail, but when things are stable, and we'll talk about when it's stable, and we still have these two major limitations that we can think of. One is it has difficulty matching complex boundaries. These problems have been resolved, but still, in general, people often think that finite difference method will have trouble writing when you have a complex domain shape. But a practical limitation is there's really much fewer software available using finite difference method for really complex physics. So now we talk about stability. Now the equation, the finite difference equation that we derived, that's this one, gives you the impression that it should work for any value of these parameters. We just choose them and we make sure we plug them in correctly, and then it should work. Now, of course, if we choose a large delta t, delta x, larger we choose, then more error in the computation. But there's something more sinister that can happen in this particular equation. It doesn't have to happen in all finite difference equations, but in this one, it will definitely happen. And that unless you satisfy the condition alpha delta t over delta x square less than equal to half, unless you satisfy, unless this is true, the computations are unstable. Unstable means you get garbage. You just absolutely get garbage. It's not inaccurate, it's just garbage. Now I want you to see a little bit contrast with calculators versus this kind of a numerical approach to this differential equation. So in a calculator, we get garbage only if we type in something wrong. Here, we can type in what seems like very legitimate quantities, alpha value, delta t, delta x square. We can type these in correctly, and we can still get complete garbage if this condition is not satisfied. This really sets aside numerical solution from an analytical solution, because we can do everything right, just the method itself works in a way that for certain conditions it can give garbage. And so we need to be prepared for that. This is something very critical to know, that to trust a numerical solution, we have to make sure that the solution has been validated. Without validation, we just cannot trust a numerical solution. So finally, to summarize numerical methods, you saw it's simple. It's really simple to develop, And we did this for heat equation. It doesn't have to be heat equation. You can take any equation and write a finite difference formulation for it. So it works for arbitrary equation. Now, it can be made as accurate as we want by reducing the distance. So if we want, the solution here is going to look, let's say, something like this. And that's not good enough. If that's not good enough for you, you want it to be even smoother, then we could add more points. We could add more points in between, and then that will give us a much smoother solution. Of course, that means more computations because you are computing at more nodes. But it can be made as accurate as we want. But depending on the method we use, and the equation that we used here happens to have this limitation that it is unstable, it can have instability in the computation. Now you can rewrite, you can come up with a different way of writing finite difference that will not have this kind of instability. But in general, there can be situations for which it can have instability and therefore give you garbage.